Thanks, Matt, for the nice introduction. Good morning, everyone. So first of all, I would like to say that it feels very good to be back there and to see you all new faces, but also colleagues that I had at the time. So it's very great pleasure. So maybe you remember in 2011 when Dr. Popovic was leading the Tuesday lecture, I already presented something about repeated sprinting, but it was more about the physiology. And today I will try to take another angle and look at the neuromechanical manifestation of fatigue during this kind of exercise. Well, let's set up the stage. So this is the Olympics. So every summer, every 4 years, we get all excited because the Olympics are coming, and the top is the 100 meters. Here you have like 100 years of history of the 100 meter sprints with the top 3 finishers. And what you can see, obviously, is like there is an increment in performance until Bolt. So this is about up to 25 meters faster than it was a century ago. Just to convince you, today the 8-year-old record would be a gold medalist in the 1896 in Athens. Just imagine. And under 1819 will be silver medalist in 1980, so not that far. So you can see that's considerable improvement in the sprint performance. So sprinting is important, not only in athletics, but also in team sport, because we have to repeat this kind of intense and maximal action. And this is also the focus on some trainings, such as the repeated sprint, that can be done also in hypoxia, which is something I'm interested in, but I will not be presenting this today. We'll stay focused on the running mechanics. So sprinting can be defined as all-out performance, usually 10 seconds, so you can maintain the performance, and then after it decreases. But for the purpose of this talk, we will focus on effort up to 30 seconds. So how do we define the repeated sprint ability? This is the ability to produce the best possible average sprint performance over a series of sprints, and the recovery in this time is incomplete. It's important because it means that if I have a pointer, yep, the performance here in red is decreasing over repetition. You cannot maintain because it's incomplete. And there's a distinction to be made here with the intermittent sprint, where the recovery is longer, 2 to 3 minutes, and then you see that the sprint performance can be maintained. So today we will be focused on this one, when the recovery is incomplete. And this is crucial because it has been collected with the distance that can be covered during the matches. So here's the puzzle I would like to assemble with you today to try to get a better picture how looking at this, neuromechanics can improve repeated sprint performance. So let's start with some background about some mechanical variable of interest that we'll be talking during this presentation. So what is neuromechanics? This is something clean that you are very familiar, but maybe not everyone. This has been popularized by Professor Enoka in the US. So this is 2 disciplines, the neurophysiology and the biomechanics. And why is that important? Because it improves our understanding of the internal and external force so that we can try to improve the performance, reduce the injury, improve the footwear, the safety of the athletes and the practice. All right, so looking at how we interact with the ground, we can obviously measure the kinetics, so the contact, flight time, and so on, but also the ground reaction force. And using the ground reaction force, we can model the behavior of the legs. It's what we call the spring mass modeling. So basically, our leg acts as a spring. During the contact, this is compressed and then recoil during the push-up phase. And we can measure the force acting at the ground level, and then we can have an idea about the force and then the velocity and the displacement of the center of mass to try to measure the stiffness. So stiffness literally is the resistance of an object to a body change in leg length. So we can quantify basically 2 stiffness, the leg stiffness and the vertical stiffness. So the leg stiffness is the ratio between the peak vertical force that we can measure with the force plate and the leg change, assuming that's the position when you're standing like me now, and then the difference when you reach the lowest point at the mid stance. Then when you make the ratio between this force and this displacement, then you get the leg stiffness. This is the total stiffness of the leg spring during the stance. And basically, when you increase the speed, and this is true in humans, but also in animals, the leg stiffness doesn't change much. It only changes when you are running on compliant surfaces. This is increasing, you can see there in this instance. Or when you have unnatural running speed, such as for a given speed, if you increase the step frequency, then you can change the leg stiffness. If not, it's very relevant to change in speed, sorry. We can calculate also the vertical stiffness, which is the ratio between the peak vertical force and the center of mass vertical excursion. And this is sensible to change in speed. And this basically increases with the increase in speed. All right, with this in mind, let's move on. And I will try to present you several studies that we have conducted over the past 5 years. I will start with one that I've conducted in Aspetar, in Montpellier, back to France. So I was already interested in this before to come here at Aspetar. So yeah, in France we are lucky. We had the 200-meter track, and we got 5-meter force plate here. So what we ask is our team sport player to run back and forth 12 times. So 6 times odd sprint number and 6 times even sprint number. So the force plate, they are located here. So in one direction, you can get the 5 to 10 meters, and on the other way, the 30 to 35 meter distance interval. So the idea was to see if there was an effect of fatigue, and if the effect of fatigue was dependent on the distance interval, right? So here is the time. So as expected, you cannot maintain the performance, so it's lengthening, cross repetition. Here's the contact time. So obviously there are differences between the two distance intervals because of the difference in speed. You go faster at the 30, 35 than the 5 to 10. Here's the stride frequency. It's decreasing. The stride length is not changing, but obviously again some big difference due to distance interval. But the point that I'm trying to make here is that fatigue has no, the distance interval has no influence on the fatigue-related effect. They are the same magnitude between the two distance intervals. Here's 2 traces of the horizontal ground reaction force for the first and the last sprint. So you can see that first there is asymmetry, but this we will come back to this later during the presentation. But here I want to show that the peak braking force and the peak push-off force is decreasing with fatigue, but once again this decrease is the same no matter of the distance interval. We calculate the vertical and leg stiffness. So as expected, vertical stiffness decreased because the speed decreased. But what I told you is like the leg stiffness is not changing, and this is what we verify here also, with again some difference between the two distance intervals. And we observe a nice correlation between the stride frequency and the vertical stiffness, which means that if you want to improve your repeated sprint performance, maybe we need to pay some attention to try to minimize the increase in contact time or the decrease in stride frequency with some training to try to best improve the repeated sprint ability with a better maintenance of the stiffness level. So that's the first clinical, practical message. Well, this is with expensive equipment, force plates, but the good news is that if you accept that we can modelize the vertical signal during the ground contact, with the function, then we can have an idea about the stiffness using field-based measurement. If you only measure these parameters, so very simple one, the leg length, the body mass, the flight and contact time, that can be with the PIDAR system, for example, which is a contact mat, basically, and the velocity with the radar gun, then we are safe. We can evaluate the vertical stiffness and the leg stiffness using this equation, just replacing this in this equation. So this opens doors for spring mass modeling in field condition for many number of steps, because the force plate, we got only 2 steps, only 5 meters. But this you can do for the whole duration of the sprinting. And this is what we did. So we work with Al Ryan under 19 here, and we work also with the Qatar national team to conduct this kind of experiments. So every time 6 sprints, here 20 meters, 20 seconds rest, and something more demanding with the national team, longer and shorter, so different work to rest ratio. What we did is that we fit their soccer boot with this PIDAR system to measure the flight and contact time and have an evaluation of the stiffness regulation for this player across the sprint repetition. Here are the results. So what you have to look at is only this. What we observe for the first one, so 6 times 20 meters with 20 seconds rest, is that the contact time is increasing. the stride frequency is decreasing, but it was not significant because the sprint decrement, which is the difference between the first and the last one, was quite narrow. But then when we replicated this with the national team, with something way more demanding, you can see that the sprint decrement this time reached about 10%. We reached the same figure, but with a larger magnitude of change. So this time the contact time is increasing even more. The stride frequency decreased significantly, but the stride length, you can see in both experiments, didn't change. So really what decreases is the frequency. It's quite consistent between the two studies. We also evaluate the stiffness, and once again, so maybe the scale can be a bit misleading, but what you have to recognize that the vertical stiffness is decreasing in both, and the leg stiffness, again, is not changing. And why is the vertical stiffness decreasing? Remember, the vertical stiffness is the ratio between the peak force and the vertical excursion of the center of mass. This is essentially because of the center of mass vertical excursion, because the peak vertical force is not changing much. So the cool thing with the PIDA is that you can also measure the plantar pressure distribution. So where the force acts on the surface of the foot, how much, and does it change with fatigue? This is what we thought, but this is not what we observed. You can see that this is the foot in 9 different zones that are illustrated here. And you can see that from sprint 1, 2, 3, 4, 5, 6, that it's quite consistent. There is no change in the plantar pressure repartition. And we observe the same thing for the more severe exercise with a more forefoot pattern. Right, let's go to our third piece of the puzzle. So I'd like now to talk about the instrumented sprint treadmill. So let's take a step back. So the first attempt to try to measure the sprinting speed and the split times was by Hill in 1927, where this athlete was wearing a magnet that was recognized by this call here, and this they can track like the speed at a different distance interval. And then came up Franklin Henry, where it was like the ancestor of the photocell gates, and you can see it was something that has to touch and then like probably send some signal. Now obviously we have more sophisticated equipment, electronic, that can be used by everyone, not only elite athletes, you can see for sure. So yeah, the good thing is that we can measure the kinematics, especially with this, also with the opto jump, quite easily, but we have no idea about the kinetics of the force acting on the ground, how you produce the movement. So that's why we need to move to the lab also to get some treadmill, and the first sprint treadmill was basically 30 years ago in 1987, and with a tether here attached to the wall, it was possible with the cell to measure the horizontal force, the treadmill speed, and then you can get also the power, which is the product between the speed and the horizontal force. So things have changed in the year 2000, especially in the US, in the lab of Roger Cram, who is a big leader in this field. He developed some treadmill where you can measure both the vertical and the antero-posterior horizontal force. This is Pistorius, for example, that was tested in this lab. So this time we really measure the force at the foot level and not with the cell that is attached to the back. I have here a video just to figure out. So that was the thing. They have to catch the rail and then jump on the treadmill at full speed. So yes, you can have top speed. Here you can see it's quite fast. Yes, you can measure the ground reaction force, but because you have to jump on the treadmill at full speed, you cannot get the acceleration kinetics, only at top speed. And this is quite a big limitation for if you want to investigate the sprinting. So at that time, yes, we had the sprint treadmill. We were able to measure the 3D force, but we are only able to reach the top speed, not the acceleration. Then came all the Woodway and stuff, where you can measure all acceleration, but you don't have 3D force. You have the force, and that's not measured at the level of the foot. So it's a little limitation, huh? You would agree. So if you want to evaluate the velocity, force, and power, of course we can do that on the bike. But when we want to test the athletes, team sport, sprinters, what's the relevance of this? So that's why we came up with this idea to validate the device that accumulate all this feature to be able to have like the track the whole sprint kinetics, the 3D force to reach a decent speed. And thanks to a grant from Qatar National Research Foundation, I got the money for the procurement of this treadmill. Here's the treadmill and the validation paper. So you have two modes. Of course, you can run at constant velocity mode and then get the running mechanics. But also you have this constant torque mode that allow you, with the correction of the torque factor, to sprint like you will do on the field. Here's one example. For example, so the subject is attached behind, and then you can really accelerate and track like almost like if you're on the field. So the good thing is that you can record the 3D, especially the anterior-posterior, during the whole acceleration and top speed, and you can reach almost top speed. I say almost because when we compare this to the field, it's 15% less on the treadmill, but the kinetic is exactly the same. So that's good news. There is very strong correlation. So yes, the speed, they cannot be the same like on the ground, but it's good reflection because there is good correlation. And this has been experienced by top level sprinters. So two treadmill of this kind in the world. The first one in France, in Saint-Etienne, with Professor Morin, and then the second one here at Aspetar or at Aspire with our colleague in the biomechanics lab. So here, some example of the trace that you can get. So you can get instantaneous traces of the ground reaction force in all directions with the speed. So it looks something like this for a sprint of 4 seconds. And then you can average for each step, and then you get something like this for the change in velocity, force, and power. For example, 6-second sprints, so it's about 20 steps. So, right, the first thing that we want to do is to verify the reliability, right? Because when you have equipment like this, you want to be sure that if you see a change with an intervention, it's not due to the noise. So it's quite busy slide, but don't worry. If you're interested, you can always get back to the paper. But what I want to show you is that on the left is the intra-session, on the right is the inter-session, so the same day, a week apart, for many parameters. So the things to remember, I think, is that for the kinetics, you see that the reliability is way better on the vertical than the horizontal. It's 3 times larger, and this is the same figure for the intra and inter-session. So more variable in the antero-posterior. And also 2 times larger variability for the inter-session compared to the intra-session for almost all parameters. So this is something to consider when you want to have intervention, like a training. You need to have like a decent sample size if you want to be able to detect some meaningful difference. Right, with this in mind, so we are confident that we can track some change, and then we ask some runners to run 3 distance, 100 meters in black, 200 meters in white, and 400 meters in gray on this treadmill. So the beauty is that we can track for every single step all the running mechanics with the change in speed. And it is a direct comparison also, because in the literature you have some paper focusing on different distance, but nobody in the same study, in the same subject, compared the 3 distances. And this is what we tried to do. So what we did is that we average, of course, the steps, and you cannot have comparison of all single steps, about 50-meter distance. And we all reference to the first 50-meter distance interval. And you can see that the change, obviously, they are larger with the increase in the distance. And this is also what we observe with all the running mechanic stuff. I'd like you to focus only on few. For example, the contact time, you can see that from the 100, 200, and 400, the increase in contact time is way larger. With the increase in distance, the same in frequency, the decrease is larger, and the change in stiffness as well. Right. We also wanted to go a bit more further and to have some comparison, some relative comparison. So we also normalize everything to the distance interval, 25, 50, 75, and 100% of the distance interval for all the for the 3 sprint distance. So if you take, for example, the half, so 50% of the 100, 200, and 400 meters, you can see that the running mechanical alteration, they occur earlier in the 400 compared to 100, and to a lower extent to the 200 distance interval. This is only the contact time, but all the parameters, they show the same figure. So the message here is like when you make a relative comparison between these 3 distance, the change, they occur relatively earlier with the longer sprint distance, the 400. Right. So I said I will not talk much about environmental stress, but still, here are a few slides. Cool. So this is good opportunity to say thanks to many people here, like all my subjects, mainly the guys from the Excellence in Football that are sitting there. Thanks, man. You are here. So yeah, what we were interested in is to see if you execute this repeated sprint exercise in the heat, do you have like larger change in performance, and what explains this? What's the mechanical basis of this possible change? So we ask 14 athletes, yeah, it's correct, to conduct this kind of protocol, 3 sets of 5-second sprints, 1 time in cool, 1 time in the hot condition. So here is what we observe. For every single sprint, you can see that obviously you have a decrease in the performance, and that decrease, that overall sprint performance is lower in the heat, and especially in the set 2. This is even more showing, sorry, here in this slide. You see that across sprint you have a decrease, and then this is especially lower in the heat during the second sprint. So we measure also some physical measurement, and as you can see, the increase in core temperature was larger in the heat, but it's quite striking that even in the cool, you can see you can reach like about 39 degrees, and this is probably because we implemented a strong warm-up, something that's really match what's done on the field and not what's done in most of the studies where you only perform 10 minutes warm-up and then 3 sprints and there you go. Like, I don't think you're ready for the challenge. So we really try to push the participant, and this is probably why we observe such unexpected increase in the cool condition. So as expected, very large difference in the skin temperature, and also all our markers of physical strain and perceptual strain were also larger in the heat. Also the thermal comfort was also larger in the heat. So why is the decrease in the sprint performance larger in the heat? So this is the beauty with this treadmill. You can get some clue. And as you can see, the horizontal force is quite matching the speed, and then probably it's one of the factors explaining why you go slower with sprint repetition in the heat. And so is the power output also. And you can see also the contact and the frequency. So are 2 main parameters that are always changing. Here it's also consistent. When you stress more the system with the heat exposure, then again, the increase in contact time or the decrease in stride frequency is changing. So this is quite consistent. Of course, we try to do that in hypoxia. So this time, one of exercise in normoxia, moderate and severe hypoxia. The severe one was about 3,600 meters, so we wanted to replicate Bolivia compared to South Africa, let's say. Here are the results. So across sprint repetition, of course, you have a decrease in performance, but sprint 1 is the same. So as expected, when you do 1 single sprint in hypoxia, no matter the level of the severity of hypoxia, you can match the normoxic condition, but then the recovery is obviously impaired, and then you cannot sustain this, and then you have larger and earlier decrease in performance. And why is that? Once again, here I've plotted all the kinetics, and this is quite clear, like the change in the vertical force, they are quite small and not different between the condition. The horizontal force, you can see they are 3 times larger, and they are especially larger in the condition creating the more severe fatigue and the propulsive power as well. So that's really important message there. What is changing is the horizontal, is not really the vertical, and this is what makes the difference with the severity of the stress. And once again, very consistent. You can see that massive increase in contact time, but this increase again is longer in the severe hypoxia. The stride frequency decrease is larger in the severe hypoxia. And again, the stiffness is decreasing even larger there. And why is that? Remember the first study, back to France, was because of the center of mass vertical excursion. So we really confirm what we observed earlier. So the last picture about environmental stress. Right, this is a 45-meter long hypoxic marquee that was installed across the road, and now we are like working with Sven and Matt and my colleague from the department to try to find a home for this piece of equipment. So what you can do with this is that you can do some sprinting in an ecological manner, because you are on the football pitch directly. So yeah, what we did, we invited 30 team sport athletes to stay in the dorms, so they're all exposed to more than 200 hours of hypoxia for the 2 weeks camp, and then we added 6 repeated sprint sessions during this 2 weeks camp. One group was doing the sprinting at 3,000 meters, and one group in normoxia. And what we observed from pre to post the camp is that the group that did in hypoxia, they increased the sprint performance, so they decreased the accumulated time over the series of sprints, and this decrease was 2 times larger in the group that did the sprinting in hypoxia compared to the group we did the sprinting in normoxia. And the better thing is, even when we post-tested them 3 weeks after, we saw that the performance increment in the sprinting was maintained in this repeat sprint in hypoxia, but it get back to the same in normoxia. Right. So before and after the camp, we are also interested to see like if there are any change in the running pattern after implementing this kind of repeated sprinting. And the answer is no. Like we tested them at different speed, 10 to 15, at very high speed, 20 meters, and then the running mechanics were strictly the same for all parameters. This is very striking. But we also collected the data with the opto jump during this exercise, and now we're analyzing the data. So maybe it will be more specific to this exercise, and maybe we'll see some change. But if you test at standard speed, then we didn't observe anything. So right, I think I'm quite on time for once. So I will finish with some perspective. So for me, this is the most exciting part, and probably for you as well. Maybe a lot of opportunity to work together. So yeah. So this study was not done on the treadmill that is that Aspire. It was done on the Woodways, a collaboration with the New Zealand. So it's a 6-second sprint, and we're interested in quantifying the asymmetry between the strong and the weak leg during the single sprint in non-injured athletes. So here is the trace for the vertical force, and here's the trace for the horizontal force. We separated the 6-second sprint in the acceleration, the first 10 steps, and the maximal velocity, the following 10 steps. And what we observe is that the asymmetry is small in the vertical force, and it's the same figure in the acceleration and in the maximal velocity. But the asymmetry is larger if you look at the horizontal force. This is this time large difference. But it's the same between the 2 distance intervals. So again, we confirm this. So the message is that, yes, the asymmetry looks like in a single sprint in non-injured athletes, it's larger in the horizontal force compared to the vertical force. Even so, you have some degree of asymmetry, right? So this is even showing better on this figure, where you have like the vertical force, the horizontal force, so the acceleration, first 10 steps, then the 10 following steps. Again, we confirm like asymmetry on the vertical force, no matter the phase, is quite low, less than 5%. The range is also very narrow, and no one was above this 5%. Again, non-injured athletes, single sprint. But look at the horizontal force. This is quite amazing. Huh? This is 3 times larger. And look at the range, like some they go up to 30%, non-injured athletes. So yeah, the message here is that in an injured athlete, magnitude and rate of asymmetry in the acceleration and the top speed phase is way, way larger, 3 times in the horizontal compared to the vertical. That was single sprint. What happened if you repeat the sprint? So we did this experiment this time in Qatar, and here you have like different kinetic parameters, sprint 1 to 5, and same picture, the asymmetry in the horizontal is 3 times larger than the vertical. So once again, we confirm. Yeah. So if you look at the kinematics, a range of parameters, you can see that it's quite different. Then, if you take, for example, the swing time, it's only 1% asymmetry. It's quite narrow. But if you look at the flight or aerial time, it's way, way more larger. So a very big difference depending on the parameter you are looking at. But no effect of fatigue. The asymmetry stayed the same from sprint 1 to sprint 5. So this is another message. And when I was writing this article, I had some reading, and I saw that in literature somehow you can find this 10 or 15% threshold above which then you are like more subject to get injured or something like this. But when you see something like this, I don't know if you can really rely on this, sorry, because you can see that depending on the parameter, it's very much different. So using a single value, I don't think it's a good idea. And then, like, if you want to have valid comparison between individuals, that's for sure you need to use the same parameters. All right, I'm almost done. So this is a study that was conducted this time in, I'll come back to this later, that was conducted at constant velocity. And this is a trace of the antero-posterior force. You can see that, once again, 3 times larger on the antero-posterior. So we are not the only one to find this result. It's quite consistent. And the same thing in the injured athlete. You can see that this time, this is amazing, huh? Like the vertical asymmetry in the injured athlete is the same like the non-injured athlete, but in the antero-posterior direction, you can see you can reach like 45%. So this is very sensitive. So maybe we are wrong if we only look at vertical force production. Maybe when we are interested in asymmetry, we should better look at what's going on than the antero-posterior. This time, this is with injured athlete hamstring. Huh? So yeah, try maybe to separate the force. So now we need obviously to go deeper, and to do that we can thank Mr. Klein, for example, for the nice figure. To try to understand what's the joint action, what's the neuromuscular basis with some EMG measurement behind that, to try to understand what caused this asymmetry. One of the last study I want to present you today is something that you will probably do with your players in the field, like this 36 times, 30 seconds exercise at quite high intensity, about 20 k an hour, and 30 second rest 6 times. So when you do that, from the first to the 6th repetition, you can see this time the speed is constant. But you can see that even so the speed is constant, you have change in the running mechanics to compensate for the effect of fatigue. Yeah, and what is important also is that this change, they occur very early. You can see that already on the 3rd interval, you already reach the mechanical adjustment. You can see this is after 6, this is after 3. So you can see it's pretty much the same thing. So it's this change in neuromuscular function, some compensatory mechanism, they occur very early to cope with the fatigue. Yeah, so I was very interested in this variable, the loading rate. This is increasing here. Right, so if we come back to this adult treadmill, the good thing with all the steps that you can measure also the ratio of force. So this is an index of the force effectiveness. So this ratio of force is basically what's the contribution of the horizontal force to the total force vector. So obviously, as you increase the speed, then at the beginning you push a lot horizontal, and then you verticalize. You just come like this. And what happens with the fatigue is that you are less efficient to continue pushing forward for a long time. So you reach this position quicker, and then you don't push very much forward. So looking at the slope of these two can be quite interesting, and then it can be interesting also to set up some training. So this is something that's getting fashion, some added resistance, and using that with different load, can we increase the force here? Can we increase the velocity here? To which extent? Maybe we need to have individualized profile, and then after try to work with some different loads to see how can this change. And definitely this is something that we can work all together with some clubs and implement some training to try and verify this. So let's wrap up. This is Christophe Lemaitre. He was also trying the adult treadmill. So yeah, this is the message I want to give you today. So obviously, if you want to be quick on the sprint, you need to produce force, mainly in the lower limbs, of course, but you need also a good core to transfer this force. So yeah, the main thing is that you need to effectively transfer the force, and be able to do that many times if you want to be a good athlete. And this is what William James said a long time ago. A chain, and this is my view, is no longer stronger than its weakest links. And no matter the strongest links, if you have a weakness, you can be very strong, then you will not be a good football player, let's say, to be able to replicate this. So really, what's important, yes, is to produce some level of force, but more important even is how you apply this, and how, with the fatigue, you are able to maintain this force application effectiveness to continue to be efficient. Right. I'm finished. I just want to thank you for listening today. I would like to thank colleagues from my department that helped with data collection, and then looking forward for next project. Look, I want to thank all the participants of the study. Thanks to be there. All the academic partners, let's say. Yeah, I used to think I was this guy there, you know. I say was because I hope I will not be anymore in the near future, thinking like, you know, I have my ideas, I'll do my research, and, you know, like, leave me alone, I'm too busy, I'm like working on my stuff. But then, and even more now that I'm back here, like, I realized like this guy is so important, and this guy is probably you guys, the clinicians, because you will give us some clue, you know, to better understand the practice. And I like to thank many people here, like especially the podiatry department, because I will be able to do the placement there to better understand like my research and connect this to the real world. Also colleague from Aspire, also colleague from Aspetar, Karim, Anissa, I know you use the, where are they? Yep, you use also the treadmill also in Aspire. I know that you're also using the treadmill to check some asymmetry. With Qatar University also, we have some project with Qatari, also exercise medicine, how we can unload the obese participants. Yeah, so exciting time. Thank you.